Have you ever seen a car engine start with just a key twist? Or how an MRI machine captures detailed images of the human body? Behind these marvels lies a simple yet powerful device, the solenoid. A solenoid is nothing but a long coil of wire wound tightly in helical loops. When you pass electric current through it, something magical happens. It creates a magnetic field that behaves just like a bar magnet. Now here's where it gets interesting. If we insert a core, especially one made of ferromagnetic material like iron, the magnetic field inside becomes dramatically stronger. Solenoids aren't just theoretical tools. They are the core of electromagnets, relays, switches, and even the ignition systems in vehicles. You'll find them all around you in devices that convert electrical energy into magnetic and mechanical motion. Take a moment to observe the diagram. You'll see a cylindrical coil, arrows showing current flow, and magnetic field lines threading through it. That's your solenoid in action. Let's now explore what's really going on inside a solenoid. The magnetic field formed inside an ideal solenoid is remarkably uniform. All field lines run parallel, equidistant, and in the same direction. And the best part? You can determine the direction of this magnetic field with the right-hand rule. Curl your fingers in the direction of the current loops, and your thumb points in the direction of the magnetic field. Inside, the field is strong and straight. Outside, the lines loop gently back, just like a bar magnet's field. This is why solenoids are often described as magnetic dipoles. They develop a north pole and a south pole depending on current direction. Take a look at the diagram here. Field lines are dense inside the coil and looping back on the outside. The resemblance to a bar magnet is striking. Now let's bring in the maths. How do we actually calculate the magnetic field inside a solenoid? Here's the formula. B equals mu Ni, where B is the magnetic field in Tesla, mu is the permeability of space, N is the number of turns per unit length, and I is the current flowing through the solenoid. It's important to note the field does not depend on the radius of the solenoid. Only the current and how tightly the coil is wound. Now, if the solenoid has a core made of magnetic material, replace mu naught with mu equals mu naught times mu r, where mu r is the relative permeability of the material. Let's plug in some values. Say we have 1000 turns per meter and a current of 2 amperes. Then B equals 4 pi times 10 to the power minus 7 times 1000 times 2, giving approximately 2.51 millitesla. You may be wondering, is a solenoid really that similar to a bar magnet? Absolutely. When a current flows through it, one end of the solenoid becomes a magnetic north pole and the other becomes south. This is because the magnetic field lines flow out from one end and loop back into the other, mimicking exactly what we observe in permanent magnets. If you reverse the current, the poles reverse too, a key feature that makes solenoids useful in applications like magnetic switches and motors. Have a look at the visual comparison. The solenoid's field lines outside loop from north to south and inside from south to north, just like a bar magnet. This analogy helps us appreciate how electric current can generate magnetism, not just in theory, but in real devices we use daily. Let's step into the real world. Where do solenoids actually make a difference? In medicine, MRI scanners rely on powerful solenoids to produce high-resolution internal images. In engineering, solenoids are used in electromagnetic valves, door locks, and automotive starters. With a flick of current, these devices turn electrical energy into motion. In electronics, solenoids help design inductors and transformers, essential for voltage regulation in circuits. Whether it's a robotic arm or your washing machine's water inlet valve, chances are a solenoid is doing the heavy lifting behind the scenes. Let's put all this into practice with a quick problem. Imagine a solenoid 50 centimeters long with 1000 turns carrying 2 amperes of current. What's the magnetic field inside it? Step 1. Let's calculate number of turns per unit length. N equals N divided by L is equal to 1000 divided by 0.5 is equal to 2000 turns per meter. Step 2. Use the formula. B is equal to mu naught times N times I. Substituting values. B is equal to 4 pi times 10 to the power minus 7 times 2000 times 2, which gives us approximately 5.03 milliedslar. And there we have it, a real calculation showing how powerful a solenoid's field can be, even with moderate current. Let's quickly revise what we've learned about solenoids. A solenoid is a simple device, just a coil of wire, but it generates a uniform and controllable magnetic field when current flows through it. Its magnetic behavior closely resembles that of a bar magnet, with field lines, poles, and dipole characteristics. The strength of the magnetic field depends on current and the number of turns per unit length, and this relationship is captured in the elegant formula, B equals mu Ni. From MRI machines to electromagnetic relays, solenoids are everywhere, bridging electricity and magnetism in practical, everyday technology. I hope now you have a clear understanding of how solenoids function and why they're such vital components in the modern world of physics and engineering. See you in the next session with another fascinating concept of electromagnetism.